Okay, so welcome students. Today we will learn about the speed performance of induction motor. Now we know that there are various methods to control a motor speed, like stator voltage control, stator frequency control, stator V by F control. There are several various methods are available to control a motor speed. Now, in today's experiment or today's learning, we will discuss about how to obtain speed control performance of induction motor using V by F control technique. So this is the hardware design for a motor speed control. I would like to explain each hardware importance and the requirement of hardware. Okay, so as we know that before I start going to hardware, I just explain that how the block diagram is represented to control a motor speed by using V by F method. So for a here, this is the motor, induction motor, which is coupled with the electrical load like a DC motor coupled with a resistive load. Okay, so if we vary the resistance or armature resistance, we are providing a loading to a motor. Okay, so that loader, the DC motor is work as a loader as a to a induction motor. Now again, motor is coupled with a speed sensor to measure the real time actual speed of motor rotor shaft. Okay, again the motor is supplied through an inverter. As we know that we will design a system for a V by F method. So here the inverter is required to convert a DC fixed DC into a variable output AC supply. Okay, so by using a V by F method, we can control a stator voltage and stator frequency by using a controller or 6 IGBT pulses that will providing from a DSP controller. Okay, now for a fixed DC, again we have to use a DC AC to DC rectifier, and this is diode rectifier which convert the 3-phase AC into DC, and this DC is connected to your DC link capacitor. Again the DC is given to your inverter, so that the inverter will convert that DC fixed DC into variable AC output voltage and frequency. Again the frequency, the speed is measured from a speed sensor. So here we attach a speed sensor which is called as a speed encoder. Okay, so that encoder is giving a speed or pulses of output in the reference of input speed. Okay, so now the pulses is converted into the pulse frequency is important, and the pulse frequency is calibrated and scaling in the terms of RPM. So we need a software to program an algorithm to develop to sense the input speed as well as to sense user command from user interface. So the DSP controller is responsible to give a reference to our motor as well as sense the speed. Okay, so here for a closed loop operation we require to make a PID control over here. So make an algorithm in a DSP controller, and the DSP is generated a command signal or control signal to your IGBTs. Okay, and then PWM is generated. So here sine PWM is generated from the algorithm, and this 6 PWM is given to your bridge 3-phase bridge inverter. Okay, so this is our block diagram. Now I just figure out which block is represented which one hardware. Okay, so first one, if you see here, this is the motor. Okay, motor coupled with DC motor load. So here the blue one is your induction motor, and the yellow one is your DC motor load. So DC motor is this is separately excited DC motor, and this is separately excited by a here DC rectifier power supply here, which is supplied from your line supply. As well as this is 1 HP motor. Okay, and rated RPM is 450 RPM, and the voltage line to line is 440 volt. RMS voltage is terminal voltage of motor. Similarly, this is DC motor load is also 1 HP motor having a 1500 RPM. Okay, so now this is coupled with a shaft, and a speed encoder is placed to its rotor shaft, and the speed is measuring from this encoder and again filtering this input signal by a various noise, and after they filter out the noise, we can feed this signal to our DSP. So I think this block is clear. Now inverter section. Okay, so here this is the power module. Okay, so in this power module we want a AC/DC rectifier with inverter. So if you see here, we have this inverter stack. This is Semicron company stack. So now if you see, there are a bridge three-phase rectifier is there. Now this rectifier is convert the three-phase AC into DC. This DC is connected to your DC link capacitor, and this DC is also connected to your terminal voltage of your inverter. So now we use a three arm or three leg 6 IGBT bridge inverter to give a three phase supply from these terminals. So now this is our output terminal. So this is our power module. Okay. As well as if you see, this is our power assembly in which power module is there, power converter is there, power motor is there. Now for shifting from high power to low power side, we require here is a isolation to provide a voltage isolation or optical isolation between a low voltage supply between high voltage. So this is the circuit for your isolation. Here this is reference kit to measure the input voltage, input current for developing for a higher algorithm like vector control or DTC control of induction motor. We require this, but for a V/F method, we not require this type of sensor interfacing, because we not need to measure a line voltage and line current or DC link voltage from this application. Okay, so it is just used for a higher algorithm. We can use this. So isolation is provided from your level shifter card. So here in this state you see here, this is our DSP card. So in this small chip is here to program into DSP by using your PC or some any system. This program is successfully debugged from your JTAG emulator, as well as the output is communicated. The output speed as well as output current across from the sensor kit can be shown from user interface from a RS232 communication, or you can say that by using USB port communication to your system. So here now this is our DSP card. So DSP have programmed from your system by using Code Composer Studio or either from your MATLAB. Okay, so here initially we use a MATLAB to program to debug a V/F control algorithm in DSP. Again, we need to measure a speed. So here this is the speed signal. Okay, so speed signal is given to DSP and reference is given from user interface. So this card is given a reference. There are some limit switches are there to speed enhance and decrement of speed. So if you press this switch, up switch, then the speed is up of motor. If you want to down decrement in speed, you just pressing this speed by some figure. Again, this PWM is given from a level shifter card. The level shifter card is converting this 5 volt PWM into a 15 volt PWM signal. Okay, and provide a optical isolation between higher and lower side. So this PWM is now putting to your inverter state from here is a IGBT gate signal, gate terminal is there. So we use 3 legs. So in each terminal we can provide IG1 and IG2, IG3, IG4, IG5 and IG6, means in each terminal we will fire 2 IGBTs at a time. Okay. So similarly, this is the complete connection diagram. Here is our DSO to sense our input or output characteristics of voltage and current waveform. Similarly, this is our power quality analyzer to sense the line voltage, line current, as well as frequency and harmonics, and analyze various parameters about motor. Okay. So now I think the hardware specification or introduction about this hardware is completed. So now I just use to I just run this. I just provide a input power to motor and see that how the motor will respond or catch a speed, okay, to a desired speed. So by using a MATLAB, if you see here, this is our program window from MATLAB. So we just use a various variable and as well as GPIO switches, as well as capture pin to sense the speed, okay, as well as some interrupt services when we want to see how when PWM is fired, then we need to measure a current or any other interrupt if we want to see that which type of interrupt is given to your system. So again the system is fired according to, okay, the interrupt is occurred. So here if you see, this is lookout table to give a constant firing, okay. So if you see how V by F is possible in a DSP, so now if you see, this is our PID controller is there is a set speed is there, actual speed is there. Now we compare this signal and give a to P coefficient and I coefficient. This is the integration, and now given a variable like PI output signal, okay. Now PI output is given to your lookout table, okay. So from this lookout table, this is scaling is given. So according to PI out, we can change the frequency over here, okay. So if you see here, from this method we can generate a V, we can vary the V voltage and frequency, and this reference is given to your EPWM block. So EPWM is nothing but it is a responsible to generate a PWM signal to a output port of DSP, okay. Another one, we want to see the what the speed is gone or given is running the motor, okay. So actual speed, so here this is the SCI transmit block is used to send the reference speed, actual speed as well as current signal. So now this is the SCI block, and so serial communication interface is possible from this DSP module. So the programming and as well as the control is very easy from this this MATLAB graphical modulation, graphical modeling. And now this is debugged through using a MATLAB, and this signal is again captured from this receiver block, okay. So here if you see, the set speed and actual speed is given, and some references there. So if I on this module, then if you see, I set the speed is here like fixed constant, constant like 1200 and something. Yellow one is your actual speed. If I change graphical interface from this port, then the speed is changed accordingly, okay. So this is real time application. So if you see, if I continuously press, then maximum 1400 is it's a constant limited switch maximum speed of motor. Now this is our actual reference, and this is our real time actual speed. Is desired speed is yellow one. If just I just on the power supply, then see that how it is motor is running and how the system is work. So again, here now voltage is 0. If you see, voltage is 0, okay. I just on the power supply using auto transformer. So now both the yellow one and blue one speed is overlapped. So now the motor is track its catch its desired speed to its actual speed is very matched to its desired speed. So if I reduce this speed, so if you see here, you see here, this is our reference speed and this is our actual speed. So if you vary the actual speed or reduce the actual speed, the speed is reflected in this our PC, okay. So now suppose that I want to run the motor at a 11,000. Okay, so approximately you can set this speed according to your desired rating. So I set a speed at a 11,000. So now this is actual speed. So again I want to reduce this speed. And it can be increased from this manner. So again, if you see here, this is our line voltage supply. Okay. So here the PWM method is used. So you can see this is a RY voltage, phase R and phase Y. So if you see here, at a start or end, the pulse width is very small, but at a peak value at the middle of this pulse, the PWM signal is, the pulses is very high. Okay. So we get a line voltage, line current in a two level output. Similarly, this is our the output voltage output as well as frequency. So you see here, when I run the motor at 1400 rpm, then if you see the frequency of the stator supply to the motor is 46.9 hertz, as well as amplitude of line voltages are like this. So if I changes the frequency, if I change a rated rpm from an input supply, then you can see we can change the supply voltage as well as frequency also. Okay, as well as speed is also can reduced. Now, if I apply a load to a motor, then see, now this is lens is on, load is on. So I need to increase the input supply because input is very less here. ज़्यादा नहीं कर सकता हूँ इसकी वजह से. As I changes the load over here, so for a proper full load I need to apply a 440 line to line voltage, but here is 300 volt, so that's why the problem is there. When I apply all load, full load, then it is reduce its speed. Okay, so now if I want to reduce the speed, you can see so now if I reduce the speed from this GPIO interface, the user can define its rated or desirable speed. So according to desirable, the DSP generates the firing pulse to IGBT and set as well as rotate the desired speed up, match each other. Okay, so now we can control the speed of the motor. Okay, there's very low range to very high range. So here you see here the motor speed is set speed is 403 and we actually rotate near about to 400. Okay, so as now if you want to increase and decrease the speed, the motor will accordingly respond. you can also log the data. Okay, so if you stop in simulation and if you want to see how the speed response is matched, so you can see here the actual, and yellow one is your actual and the blue one is your yellow one is your desirable input and the blue one is your actual speed. So at low speed motor have some higher ripple, but at a nearby it's rated, it is have a very small ripple. So we can control the speed from this method. This is the essence of this presentation, this video, that from the DYF method we can control the speed of motor. So thank you.